Ammonia or azane is a compound of nitrogen and hydrogen with the formula NH3. It is a colorless gas with a characteristic pungent smell. Ammonia contributes significantly to the nutritional needs of terrestrial organisms by serving as a precursor to food and fertilizers. Ammonia, either directly or indirectly, is also a building block for the synthesis of many pharmaceuticals and is used in many commercial cleaning products. Although common in nature and in wide use, ammonia is both caustic and hazardous in its concentrated form. The global industrial production of ammonia for 2012 was anticipated to be 198 million tons, a 35% increase over the estimated 2006 global output of 146,500,000 tons. NH3 boils at -33.34 degrees Celsius at a pressure of 1 atmosphere, so the liquid must be stored under pressure or at low temperature. Household ammonia or ammonium hydroxide is a solution of NH3 in water. The concentration of such solutions is measured in units of the Baumé-Acute scale, with 26 degrees Baumé-Acute ammonia at 15.5 degrees Celsius or 59.9 degrees Fahrenheit being the typical high-concentration commercial product. Natural occurrence. Ammonia is found in trace quantities in the atmosphere, being produced from the putrefaction of nitrogenous animal and vegetable matter. Ammonia and ammonium salts are also found in small quantities in rainwater, whereas ammonium chloride and ammonium sulfate are found in volcanic districts. Crystals of ammonium bicarbonate have been found in Patagonian guano. The kidneys secrete ammonia to neutralize excess acid. Ammonium salts are found distributed through fertile soil and in seawater. Ammonia is also found throughout the solar system on Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. Substances containing ammonia, or those that are similar to it, are called ammoniacal properties. Ammonia is a colorless gas with a characteristic pungent smell. It is lighter than air, its density being 0.589 times that of air. It is easily liquefied due to the strong hydrogen bonding between molecules. The liquid boils at -33.3 degrees Celsius and freezes at -77.7 degrees Celsius to white crystals. Ammonia may be conveniently deodorized by reacting it with either sodium bicarbonate or acetic acid. Both of these reactions form an odorless ammonium salt. Solid. The crystal symmetry is cubic. Pearson symbol CP16, space group P213, number 198, lattice constant 0.5125 nanometers. Liquid ammonia possesses strong ionizing powers reflecting its high epsilon of 22. Liquid ammonia has a very high standard enthalpy change of vaporization and can therefore be used in laboratories in uninsulated vessels without additional refrigeration. See liquid ammonia as a solvent. Solvent properties. Ammonia is miscible with water. In an aqueous solution, it can be expelled by boiling. The aqueous solution of ammonia is basic. The maximum concentration of ammonia in water has a density of 0.880 grams per cc and is often known as 880 ammonia. Ammonia does not burn readily or sustain combustion, except under narrow fuel-to-air mixtures of 15 to 25% air. Combustion. When mixed with oxygen, it burns with a pale yellowish-green flame. At high temperature and in the presence of a suitable catalyst, ammonia is decomposed into its constituent elements. Ignition occurs when chlorine is passed into ammonia, forming nitrogen and hydrogen chloride. If chlorine is present in excess, then the highly explosive nitrogen trichloride is also formed. Structure. The ammonia molecule has a trigonal pyramidal shape as predicted by the valence shell electron pair repulsion theory with an experimentally determined bond angle of 106.7 degrees. The central nitrogen atom has 5 outer electrons with an additional electron from each hydrogen atom. This gives a total of 8 electrons, or 4 electron pairs that are arranged tetrahedrally. 3 of these electron pairs are used as bond pairs, which leaves one lone pair of electrons. The lone pair of electrons repel more strongly than bond pairs, therefore the bond angle is not 109.5 degrees, as expected for a regular tetrahedral arrangement, but 106.7 degrees. The nitrogen atom in the molecule has a lone electron pair, which makes ammonia a base, a proton acceptor. This shape gives the molecule a dipole moment and makes it polar. The molecule's polarity and, especially, its ability to form hydrogen bonds, makes ammonia highly miscible with water. Ammonia is moderately basic. A 1.0 m aqueous solution has a pH of 11.6, and if a strong acid is added to such a solution until the solution is neutral, 99.4% of the ammonia molecules are protonated. Temperature and salinity also affect the proportion of NH4+. The latter has the shape of a regular tetrahedron and is isoelectronic with methane. The ammonia molecule readily undergoes nitrogen inversion at room temperature. A useful analogy is an umbrella turning itself inside out in a strong wind. The energy barrier to this inversion is 24.7 kJ per mole, and the resonance frequency is 23.79 GHz, corresponding to microwave radiation of a wavelength of 1.260 cm. The absorption at this frequency was the first microwave spectrum to be observed. Amphotericity. One of the most characteristic properties of ammonia is its basicity. Ammonia is considered to be a weak base. It combines with acids to form salts. Thus, with hydrochloric acid it forms ammonium chloride, with nitric acid, ammonium nitrate, etc. Perfectly dry ammonia will not combine with perfectly dry hydrogen chloride. Moisture is necessary to bring about the reaction. As a demonstration experiment, opened bottles of concentrated ammonia and hydrochloric acid produce clouds of ammonium chloride, which seem to appear out of nothing, as the salt forms where the two diffusing clouds of molecules meet, somewhere between the two bottles. NH3 plus hydrogen chloride NH4Cl. The salts produced by the action of ammonia on acids are known as the ammonium salts and all contain the ammonium ion. Although ammonia is well known as a weak base, it can also act as an extremely weak acid. It is a protic substance and is capable of formation of amides. For example, lithium dissolves in liquid ammonia to give a solution of lithium amide. 2Li plus 2NH3 2Lin 2 plus H2 self-dissociation. Like water, ammonia undergoes molecular autoionization to form its acid and base conjugates. 2NH3 NH plus 4 plus NH minus 2 at standard pressure and temperature. K equals NH plus 4 NH minus 2 equals 10 minus 30 combustion. The combustion of ammonia to nitrogen and water is exothermic. 4NH3 plus 3O2 2N2 plus 6H2O. The standard enthalpy change of combustion, delta H degree C, expressed per mole of ammonia and with condensation of the water formed, is minus 382.81 kJ per mole. Dinitrogen is the thermodynamic product of combustion. All nitrogen oxides are unstable with respect to N2 and O2, which is the principle behind the catalytic converter. Nitrogen oxides can be formed as kinetic products in the presence of appropriate catalysts. A reaction of great industrial importance in the production of nitric acid. 4NH3 plus 5O2 4NO plus 6H2O. A subsequent reaction leads to NO2 2NO plus O2 2NO2. The combustion of ammonia and air is very difficult in the absence of a catalyst oxide, because the temperature of the flame is usually lower than the ignition temperature of the ammonia-air mixture. The flammable range of ammonia and air is 16 to 25%. Formation of other compounds. In organic chemistry, ammonia can act as a nucleophile in substitution reactions. Amines can be formed by the reaction of ammonia with alkyl halides. Although the resulting NH2 group is also nucleophilic, and secondary and tertiary amines are often formed as byproducts. An excessive ammonia helps minimize multiple substitution, and neutralizes the hydrogen halide formed. Methylamine is prepared commercially by the reaction of ammonia with chloromethane, and the reaction of ammonia with 2-bromopropanoic acid has been used to prepare racemic alanine in 70% yield. Ethanolamine is prepared by a ring-opening reaction with ethylene oxide. The reaction is sometimes allowed to go further to produce diethanolamine and triethanolamine. Amides can be prepared by the reaction of ammonia with carboxylic acid derivatives. Acyl chlorides are the most reactive, but the ammonia must be present in at least a twofold excess to neutralize the hydrogen chloride formed. Esters and anhydrides also react with ammonia to form amides. Ammonium salts of carboxylic acids can be dehydrated to amides so long as there are no thermally sensitive groups present. Temperatures of 150 to 200 degrees Celsius are required. The hydrogen in ammonia is capable of replacement by metals, thus magnesium burns in the gas with the formation of magnesium nitride Mg3N2, and where the gas is passed overheated sodium or potassium, sodamide NaNH2, and potassamide KNH2, are formed. Where necessary in substitutive nomenclature, IUPAC recommendations prefer the name azane to ammonia. Hence chloramine would be named chloroazane in substitutive nomenclature, not chloroammonia. Pentavalent ammonia is known as lambda-5-amine, or more commonly, ammonium hydride. This crystalline solid is only stable under high pressure, and decomposes back into trivalent ammonia and hydrogen gas at normal conditions. This substance was once investigated as a possible solid rocket fuel in 1966. Ammonia as a ligand. Ammonia can act as a ligand in transition metal complexes. It is a pure sigma donor, in the middle of the spectrochemical series, and shows intermediate hard-soft behavior. For historical reasons, ammonia is named amina in the nomenclature of coordination compounds. Some notable amina complexes include tetraammonidia quack-copper 42, 2+, a dark blue complex formed by adding ammonia to a solution of copper salts. Tetraammonidia quack-copper hydroxide is known as Schweizer's reagent, and has the remarkable ability to dissolve cellulose. Diamina silver 2+ is the active species in Tollens reagent. Formation of this complex can also help to distinguish between precipitates of the different silver halides. Silver chloride is soluble in dilute ammonia solution. Silver bromide is only soluble in concentrated ammonia solution, whereas silver iodide is insoluble in aqueous ammonia. Amina complexes of chromium were known in the late 19th century, and formed the basis of Alfred Werner's revolutionary theory on the structure of coordination compounds. Werner noted only two isomers of the complex, CrCl33, could be formed, and concluded the ligands must be arranged around the metal ion at the vertices of an octahedron. This proposal has since been confirmed by X-ray crystallography. One example is the Calimel reaction, where the resulting amido-mercury compound is highly insoluble. Hg2Cl2 plus 2NH3Hg plus HgCl plus NH4 plus Cl minus. Detection and determination. This section is about detection in the laboratory. For detection in astronomy, see chapter in astronomy. Ammonia in solution. Ammonia and ammonium salts can be readily detected, in very minute traces, by the addition of Nessler's solution, which gives a distinct yellow coloration in the presence of the least trace of ammonia or ammonium salts. The amount of ammonia in ammonium salts can be estimated quantitatively by distillation of the salts with sodium or potassium hydroxide. The ammonia evolved being absorbed in a known volume of standard sulfuric acid, and the excess of acid then determined volumetrically, or the ammonia may be absorbed in hydrochloric acid, and the ammonium chloride so formed precipitated as ammonium hexachloroplatinate, 2-PtCl6. Gaseous ammonia sulfur sticks are burnt to detect small leaks in industrial ammonia refrigeration systems. Larger quantities can be detected by warming the salts with a caustic alkali or with quicklime, when the characteristic smell of ammonia will be at once apparent. Ammonia is an irritant, and irritation increases with concentration. The permissible exposure limit is 25 ppm, and lethal above 500 ppm. Higher concentrations are hardly detected by conventional detectors. The type of detector is chosen according to the sensitivity required. Holographic sensors have been proposed for detecting concentrations up to 12.5% in volume. Ammoniacal nitrogen. Ammoniacal nitrogen is a measure commonly used for testing the quantity of ammonium ions, derived naturally from ammonia, and returned to ammonia via organic processes, in water or waste liquids. It is a measure used mainly for quantifying values in waste treatment and water purification systems, as well as a measure of the health of natural and man-made water reserves. It is measured in units of mg/L. History. The Romans gave the name sal ammoniacus to the ammonium chloride deposits that they collected near the Temple of Ammon in ancient Libya. Salts of ammonia have been known from very early times, thus the term ammoniacus sal appears in the writings of Pliny, although it is not known whether the term is identical with the more modern sal ammoniac. In the form of sal ammoniac, ammonia was important to the Muslim alchemists as early as the 8th century. First mentioned by the Persian chemist Jabir ibn Hayyan, and to the European alchemists since the 13th century, being mentioned by Albertus Magnus. It was also used by dyers in the Middle Ages in the form of fermented urine to alter the color of vegetable dyes. In the 15th century, Basilius Valentinus showed that ammonia could be obtained by the action of alkalis on sal ammoniac. At a later period, when sal ammoniac was obtained by distilling the hooves and horns of oxen and neutralizing the resulting carbonate with hydrochloric acid, the name spirit of hartshorn was applied to ammonia. Gaseous ammonia was first isolated by Joseph Priestley in 1774 and was termed by him alkaline air. 11 years later, in 1785, Claude Louis Berthollet ascertained its composition. The Haber-Bosch process to produce ammonia from the nitrogen in the air was developed by Fritz Haber and Carl Bosch in 1909 and patented in 1910. The ammonia was used to produce explosives to sustain war efforts. Prior to the availability of natural gas, hydrogen as a precursor to ammonia production was produced via the electrolysis of water or using the chloralkali process. With the advent of the steel industry in the 20th century, ammonia became a byproduct of the production of coking coal.